Hi, this is Joanne Lowy. Welcome to today's webinar, Use of 3D Fluorescence for Quality Control of White Wine. I'm the Marketing Manager at HORIBA Scientific and moderator for today's event. Thanks for signing up for this webinar. We hope you find it informative. HORIBA is the global leader in spectroscopy systems, providing an extensive array of instruments and solutions for applications across a broad range of scientific, R&D, and Q&C and QA measurements. We manufacture the world's most sensitive line of flexible, simple, and affordable steady-state and lifetime spectrofluorometers. Choose from standalone tabletop systems or custom modular systems that can grow as your requirements change. This webinar will focus on practical aspects for acquiring white wine emission excitation matrix of fluorescence, since special care is required to accurately analyze and interpret it. Before we start, I want to just let you know about a few things. First, the slides will advance automatically. Next, feel free to ask questions during the webinar. You can submit questions by typing them in the Q&A box, which is on the Q&A widget at the bottom of the presentation window. You can also enlarge your slide window by clicking on the small green icon in the upper right-hand corner, or by hovering your mouse over the lower right-hand corner and dragging it to the size you prefer. If you have any technical questions viewing or hearing the presentation, just please click on the question mark Help and we'll be able to help you. Now I'd like to introduce today's speaker, Dr. Christian Coelho, Assistant Professor of Enology at the University of Burgundy, where he teaches analytical chemistry and enology practices to future enologists. Dr. Coelho studied physical chemistry applied to environmental sciences at Paul Sabatier University and Blaise Pascal University, both in France. He obtained his doctorate in 2009 in photochemical reactivity of natural organic matter. His research focuses in the chemistry of wine, and particularly on wine compounds that preserve wine from oxidation during aging. He develops spectroscopic tools, particularly 3D fluorescence to authenticate wine, and electron spin resonance to evaluate oxidative stability of wine. Okay, Dr. Coelho, I'll turn the presentation over to you.
Okay, thank you, Joanne, for this kind presentation. First, I would like to join to this webinar my colleague Michael Goncior from Maryland University, who introduced me to the Aqualog system and helped me to design this webinar for today. So, to have an overview of the webinar today, we'll talk about some knowledge you should know on wine elaboration processes. I'll give you some concepts on emission excitation matrix concerning fluorophores and Jablonski diagrams that are more theory. Then I will show you some research that is done on oenology, dealing with EEM technology. Then the methodology we should do to standardize all the wine EEM acquisition. After, I'll give you some applications during the stage of vinification that are concerned using EEM, and then applications that are also done on wine matrices. And then I finish with some conclusions. So to start, I'll give you some things to know about elaboration processes on wine. So first, the grapes are harvested generally from the end of August till the end of September. Once the berry and are mature, the pressing steps is done. You collect the must. The must is generally added with yeast in order to perform alcoholic fermentation. Then you have a step with some grape varieties where you can add malolactic enzymes in order to perform this malolactic fermentation. Generally, it is done in order to reduce the acidity of wine. Then sometimes you can age your wine in barrels, and this can be aged from 6 to 24 months. It depends of the region and the area of wine elaboration. And then the wine is put in a bottle and aged over a certain period in function of the consumer desire. And finally, they open the bottle and taste the wine, and he appreciates all these winemaking steps in this final, which is the most important step for a winemaker. Okay, what EEM can bring to the winemaker? So first I can give you some emission concepts dealing with EEM and fluorophores. In wine, I put you some examples of compounds that are present, that are highly present. For example, the tartaric acid, which is a compound at the bottom of the slide, and a flavonol, catechin, which can be also presented at really low amount concentration, and resveratrol, which is a stilbenoid compound generally present in red wines. All these compounds are not fluorescent. Tartaric acid, for example, is not fluorescent, so we cannot analyze such compound in using emission spectroscopy. Catechin is a really interesting compound because it can be you can excite it at 280 nanometers and analyze the emission at 320 nanometers. And this emission increase, of course, in terms of concentration of catechin. The same for resveratrol. Resveratrol, for example, is not the same compound, and it has a specific excitation and emission properties. You can excite it at 300 nanometers and observe it at 400 nanometers. So on the right of the diagram, you can see the concepts generally used in fluorescence. The chromophores are excited by a photon flux. It goes to an excited state. From the ground state, it absorbs this light and re-emits the light, generally at higher wavelengths. And this emission is of interest for wine, because this light is of interest because it means it is linked to the real constitution of fluorophores in wine. Well, afterwards, how an EEM is constructed. First, this EEM, so it is an emission excitation matrix, generates a 3D view of a fixed number of emission spectra acquired with varying excitation wavelengths. You can see that the EEM matrix, that is the contour plot you can see with the blue, which is mostly blue, meaning that there is no emission, and once this emission is turning from green to yellow and red, this emission is becoming more and more intense. So here, for example, you have an EEM of a white wine with a broad band which is intense from 300 nanometers to 400 nanometers in terms of emission, and located with an excitation wavelength situated around 250 nanometers and 300 nanometers. So this pattern is of interest for wine emission. Here I show you some compounds of interest that are present in wine, and you can see that there are a lot of family compounds, phenolic acids, flavonols, flavanols, like catechin we saw in the slide before, some vitamins and enzymes also that are present, and some proteins also that can be visible with this technique. So you can see all these parameters, as you understand. In order to visualize these compounds, you have to excite and at the right wavelengths and look at the right also emission wavelengths. So all these compounds are present in the wine, and you have this unsupervised technique visualizing all these compounds. Of course, you don't have any quantitative information with this view. Here I show some two visualization of EEM. Sometimes you visualize the American view, where you have the emission wavelengths on the ordinate and the excitation wavelengths on the abscissa, and the 3D view is in the third direction. The Z is the intensity, and the European view you invert the matrix, and the emission wavelengths is on the abscissa wavelengths, in the abscissa coordinate. Sorry. So now let's look at various studies that were done on wine, dealing with this technology of emission excitation matrix. Here, this paper from 2009 showing the various emission extraction matrix from Cabernet Sauvignon from Changli Chinese region. So Changli is the Bordeaux region, is the Bordeaux French Chinese region, and they show with this technique that that when applying correctly the dilution aspects of wine in order to respect the inner filter effect, I will explain you this just after. You can discriminate between vintages from this Cabernet Sauvignon. So it was one interesting pattern that such technique can bring to the wine research. After you have another study dealing with front-face fluorescent acquisition, which is done directly at the surface of the wine. You can discriminate here brandies from wine distillate. So this application was done in order to get rid of fraudulous aspects in that region. It was a study in Republic Czech. The brandy is qualitatively highest the spirit compared to the wine distillate, and you can easily discriminate both by this contour map EM methodology. Another study, which was one of my favorite studies, is that it was done by Aredo and Rodriguez in 2011. He gathers in the EM all the compounds, the fluorescent compounds that can be visible in the EM matrix, and he applied statistical treatment to a large series of EM, and considers these statistical contributions in terms of scores. You can see on the right with scores of C1 and scores of C2, and this statistical treatment enables him to discriminate appellations on red Spanish wines. So for all auditors, I advise you this paper. Another study in 2012 was done by a Chinese team, combining also statistical treatment on EEMs from 30 wines from Jiangxi province, and they observed totally different EM image. And they succeed in discriminating 5 wine producers, and these 5 producers you observe it in this hierarchical cluster analysis. Here is a fluorescence technique used on red wines, and more specifically port wine. They look at anthocyanin. That one of the anthocyanin which is highly present is the malvildin. You can see on the left, and one form that is present when it is polymerized is the pyruvic form, pyruvic adult of malvidin, which is called viticin. And these compounds have totally different emission properties. The last one presenting an absorption at lower wavelengths, and the ratio of these 2 compounds help them to discriminate the age of port wine. So you can see port wine 2011 have a ratio of 0.68, and the oldest port wine have a ratio of 0.60. So it was a really interesting study carried on these port red wines also. And final study carried recently by an Italian group. They they combine the EEM methodology with other techniques, including chromatography, liquid chromatography, and NMR, in order to have a larger database, and it helped them to discriminate with a much better robustness Lambrusco red wine. So they discriminate the varieties of Krasposca, Sorbara, and Salamino. It enables a much better data fusion. And recently, HORIBA proposed also a tech note concerning five red wines from various origins and various grape cultivar. The Aqualog system I will present you in this webinar enables the color quantification of red wines, since it has an absorption measurement that is possible. It also enables the acquisition of all these samples, and they were discriminated in terms of color. Of the French wines presented the lowest intensity and the lowest hue. The hue is an oenological parameter that is generally used by the wine professionals, and the intensity also, which represent the sum of absorbance at 420, 520, and 620. And the U, which is the ratio of 50-20 and of 520 and 420. So they are of particular importance, and the combination with the fluorescence detection enables also to totally discriminate all these red wines, and a statistical treatment also based on a linear distinction was done on these wines, and they separate five statistical components, meaning that each wine presents a relative contribution of each of these five constituents, 5 components. For example, the component C1 is more attributed to kinamic derivatives. Component C2 more to flavonols. The component C3 is more attributed to flavin 3-ols. C4 is more on the stilbene groups, and the C5, the last one, is more attributed to anthocyanin groups. And they also show that the aeration of these wines provoke an increase of this relative contribution of C1, C2, and C3, and C4 and C5 were not so much affected by this aeration. Okay, so let's now talk about the Aqualog instrument. Here I show you the instrument, the Aqualog system. So it's a spectrofluorometer. You have the xenon source, which is the light that is going to excite your sample. The light then goes through monochromator in order to excite at a specific wavelength, and arrives to the cell containing to the quartz cell containing your wine sample. And if the wine presents chromophores that are able to re-emit this light, you observe this emission of light through the CCD device you have, and this is the really big advantage of the Aqualog system, since this CCD is not present in all spectrofluorometers. Generally, they are based on photomultiplicators, and here the CCD enables really fast and sensitive detection of these photons that are present. Here I give you the way to really the material you need to perform EEM acquisition. So you see it's really really few. You need really few, not really much material. What you need is a quartz cuvette cell of 1 centimeter path length in order to pour your wine sample. I also advise you to use a standard ultra pure water quartz cuvette in order to be sure you don't it's your blank, in fact it's a blank of the acquisition. I also use a Starna quinine sulfate sample cell in order to normalize all the EEM in order to have the same intensity for all EEMs if I want to compare them afterwards. I also use a wine polyphenol mix of 1 milligram per liter. You can see this EEM at the bottom. In order to ensure EEM repeatability and reproducibility, since all your acquisition will not be done in one day. Okay, you can do that in 2 or 3 weeks, and afterwards you can interpret your data. So you need to standardize the procedure. The most you standardize your EEM acquisition, the more deeper you can go in the interpretation of your data. And the Aqualog system is well done for this purpose, since it presents really nice corrections and normalization algorithms that you can easily apply post-acquisition. Okay, here are the various algorithms and the corrections that are done. Here you can see the bulk fluorescence acquisition of wine. You have a straight line in diagonal, which corresponds to the Rayleigh, which is due to the diffusion of the solvent, and in green and yellow you see the emission of your sample. Then this is first treated in terms of inner filter correction. Okay, it's in order to avoid reabsorption of light in case of too much absorption of wine compounds. Then you mask this Rayleigh. You don't see this diagonal in the EEM. And finally, you normalize it to the quinine sulfite in order you have something corrected and normalized. Concerning the algorithm, you need to be very careful when you acquire an EEM of this inner filter effect. This inner filter effect should be corrected if you have too absorbent wine. That's what I try to explain you in this figure. You see that it was done on white wine and on red wine. When this check is done, if you observe the linearity, it means that you can easily dilute your sample. If it tends outward this line, okay, it means that you are in your inner filter algorithm is no more followed. So this dilution factor you should respect for white wine is a dilution factor of 40 till 20. Okay, till 20 times dilution of wine, the inner filter algorithm is okay, is valid. And for red wine, this inner filter algorithm that is integrated it's totally transparent when you do that, but you should control that. And for the red wine, so you can dilute your sample till 100 times, and this algorithm is still correct. Okay, this means that if you introduce your wine without diluting, okay, you will totally your inner filter algorithm will totally be will not be in the linear response. So this is what you should decide just at the beginning of your acquisition in terms of your wine. Okay. So decide this dilution factor for your wine samples in the linear response. Okay, concerning this dilution, I show you two examples of a red wine. It's a Cabernet Franc grape variety. if you dilute, so I tell you that you can dilute it, the red wine, till 100 times. So here I think I dilute it at 200 times in order to be in this linear range. I use two solvents. One which is ultra pure water. Ultra pure water has a pH of 5.5, and a synthetic wine at pH around 3.5. And you observe that the emission is not at the same intensity. So here the EMs were all acquired with the same standardized procedure I described you just before. So it means that the solvent you are going to use has an impact on the intensity and the relative contribution of each compound. Here it can be explainable by the fact that anthocyanin in red wines that are due to these flavillum cations that are present, particularly in malvidine we saw before, is colored at this wine pH. But if you use ultra pure water, you add an OH function that breaks this emission of light, and you have a less intensity. So you have to standardize that also. Here is the CCD detector. This CCD detector is also a good point on this aqualog, and you can try to change it to vary this the parameter of the integration time, which represents in fact the photon flux received by the detector. You integrate the number of photons received in a certain period that we call the integration time. And I present you here the same wine at 0.1 second, 0.5 second, and 1 second. Of course, when you increase this integration time, it means that you acquire for a much higher time. So the highest integration time you'll have, the highest the acquisition will last. It's a compromise between what you want to have and the resolution of your EEM. Here, with these three views, I advise you the last one at 1 second, which generally represents an acquisition that lasts from 2 to 3 minutes, so which is really fast for an EEM acquisition. And you have something more resoluted and presenting really good shapes in terms of contours. Okay, so now we observe all these parameters we can play to in order to have a real robust acquisition. I suggest you this for building your own wine model. You need to control the wine dilution. So I told you 40 times dilution is nice for white wine with ultra pure water if possible. You need also dilution of 200 times for the red wine, and if you can also with a synthetic wine with the same pH as the wine. Then you can introduce your diluted wine in the quartz cell, perform the EEM acquisition with the parameters that are fixed. Okay, the CCD integration time, you can fix it at 1 second. The diode, which corresponds to the excitation, you can range it from 225 nanometers till 600 nanometers. The emission and excitation slits are fixed at 5 nanometers in this acquisition. And I suggest also to you to add a quality control with the polyphenol mix in order you ensure all your EEM data acquisition all around your acquisition during the campaign you want to perform your runs. Then post acquisition of this EEM, you'll try to statistically treat all your wines that you collect in a database in order to build a PARAFAC model in function of your wine knowledge. What I mean in terms of your wine knowledge, I mean, it's you should know what type of information you would like to monitor using this technique. Okay, I show you some aspects in winemaking you can apply, but you should also use this technique by knowing what oenological parameter you'd like to control or to monitor. Then you optimize the number of PARAFAC components. This is a statistical treatment, and it can be easily done with some toolbox that can be carried in MATLAB, or there's a Solomio software also that is done by eigenvector that you can do that. And then you analyze your data. So you monitor the oenological parameters. You detect the chemical or microbiological anomalies in wine processing, if you'd like to control that. And you can follow and authentify your wine products in terms of your grape variety and grape and terroir. So here are the chemometrics that are applied to your EEM database. So this is a trilinear decomposition of the EEM matrix. The EEM matrix, I repeat, it's a combination of a three-day matrix with the excitation wavelengths, emission wavelengths, and the intensity. The PARAFAC mathematical model is written on the top of the slide. And that's this mathematical model that is used for your data analysis. It can be easily implemented with all the toolbox and the eigenvector software. And then you have to validate your model. So here I show you some components that can be extracted from the EEM. This model should be validated in terms of variability of a number of data acquisition. It has to have a high core consistency, meaning that the theory and the experimental data are the same, and you can split half validate your independent slits in order to improve your robustness. Okay, so now we'll try to look on some stages of vinification that can be of interest for winemakers when using excitation emission matrix of fluorescence. For me, each step during winemaking will lead to different fingerprints. It means that each steps during winemaking, if you take your wine, you'll have a different EEM matrix. So the idea you should have once using EEM analysis is that each step you would be interested to monitor during winemaking can easily be implemented via 3D fluorescence spectroscopy. And the idea is that after post-acquisition, if you run a statistical treatment like PARAFAC, you can have relative contributions, for example, here, statistical component 1, component 2, 3, and 4. So you have the relative contribution of all these statistical compounds in your EEM that you acquired. So these contributions are of interest for the winemaker. Here I try to apply this PARAFAC treatment in white wine and red wines, which is totally absurd, since you have totally two different metrics, but it's in order you understand really where I want to go with you. This PARAFAC treatment indicates me that red wines and the white wines are totally different. Okay, I don't need the aqualog system to do that. I can easily see it by observing the wine, by observing the color. So here you should should know that once you'd like to apply your PARAFAC model, you have to apply it properly with the good wine samples. For example, if you work with white wines, okay, make a model with white wines, because the statistical treatment will lead to various contributions of these components, and it is not really interesting in terms of model and of analysis. And in order to get deeper in the analysis of your samples, you need to have a robust and well dedicated model and acquisition of EEMs that are with the same matrix. Here you can also see that. So what I don't tell you, that these red wines and white wines were done with wines that were bottled. So I opened the bottles and analyzed them with the EM, and the one I just put you, the green one, are the wines that are wine made this year. So they are in terms of evolution, they are not bottled. Okay, so you have also a totally different view of localization of these wines. So think that when you want to build your own PARAFAC model, it's better to use it for one grape variety. And if you want to build your model in your wine you are making during the year, it's another story. So you should make your model for these wines you are making during the year. Here I show you a study we published in our lab last year, in order to show you the powerfulness of the EM of the 3D fluorescence measurements done on wine. Two vintages were of interest, and the same methodology was done during winemaking. Once you collect the grapes, you press it, so you obtain the must, and during the must, generally winemakers add sulfur dioxide in order to prevent from oxidation, and 3 doses of sulfur dioxide were applied, 0, 4, and 8 grams per hectoliter, which represents generally used concentrations of sulfur dioxide. These wines were bottled in the same manner. It was repeated in 2006 and 2007, and in 2014 we opened the bottles and tasted them. And of course, after tasting them, we performed EM acquisition on that, and we observed that the addition of sulfur dioxide impacts the signature of the fluorescent composition of wine, even 7 or 8 years later after the conception, the elaboration of wine. Here you can see that emission, located in the red part, is increasing once you protect your must, meaning that this protection is still present after several years of bottle storage. So in this, if you want more information with this study, I can discuss with you, since we also apply polyphenolic analysis in order to validate these observations. Okay, here is another story. We'd like to monitor, for example, the degree of must clarification. So after the pressing, the must can be settled at various stages of turbidity just before the malolactic fermentation. And this is of interest for winemakers, since this degree of clarification can impact the sensorial and the quality aspects of the final wine after the fermentation steps. And this EEM methodology enables for two wines, wine A, wine B, two wineries, winery A and winery B, to discriminate the low turbidity from the high turbidity, meaning that this composition of wine also is impacted by the practice of the winemaker during the winemaking. So this was done on white wine elaboration, on a Chardonnay white wine. You can also imagine to test your EEM, your alcohol system, to decide for aging your wines or not. On the left part, you have the post-alcoholic fermentation from winery A and winery B. If you decide to age your wine in bottle and in a barrel, generally it is done in barrel just before a bottle. You can monitor this aging. You have a shift of contributions of these compounds, these fluorescence compounds, and this is represented in this principal component analysis from both wineries. Finally, some winemakers are potentially attacked by a yeast that is called Brettanomyces bruxellensis, and this yeast is totally nefast for red wine and particularly in Pinot Noir in Burgundy, since it produced during its metabolism from phenol substrates. It produces ethyl phenol or vinyl phenols that are really bad aromas that have horse odor and clove smells. And generally, they produce these type of compounds above the perception threshold that is permitted. So it means that if this yeast is present in wine, you totally destroy your qualitative aspects of the wine you expect. So you can use, I propose here also to use the EEM to control that. You can see that Pinot Noir wine on the left that is not spoiled, and on the right Pinot Noir that is spoiled, has totally different contributions of these phenolic substrates, meaning that the metabolism of this yeast is in course in the winery. So you can track this microbiological spoilage in red wine. Okay, here we come to the conclusions of this webinar. I hope I show you that fluorescence is a powerful and useful tool to track wine compounds during the elaboration and the evolution. Wine EEMs are genuine fingerprints that gather information related to oenological processes. It's really easy to implement in a routine and qualitative control in the wineries. It's quite easy an easy tool to decide and monitor some oenological parameters, as I show you, and the sulfite additions or the musk clarification, or you can also detect the microbiological spoilage, for example, the one with the Bruxellensis, Brettanomyces. And finally, research done on wine fluorescence help wine producers requiring a combination of multidisciplinary approaches. Okay, I thank you for your attention, and I'd like to thank my university and my institute, Jules Guyot from Dijon, and I'd like also to thank Michael for this presentation. I'm ready to answer your questions. Thank you for your attention.
Thank you, Dr. Coelho, for your presentation. Before we get started on the Q&A session, just a reminder that to submit questions, simply type them in the Q&A box, which you can find by clicking on the Q&A widget at the bottom of the presentation window. Okay, our first question is, many wineries rely on UV vis and color analyses for many aspects of product evaluation. Noting also the Aqualog can make both UV vis, color, and FEM measurements simultaneously, what's the advantage of the fluorescence EAMS and analysis compared to UV vis and color analysis?
Okay, well, I really see a lot of advantages of this Aqualog system, combining UV visible spectra and EEM. First of all, in one acquisition, both fluorescence and absorbance are available from one wine sample, which really presents a saving time aspect. Afterwards, it is important for the color intensity and hue measurements. I also see in terms of technical aspects, even if the Aqualog system presents good algorithms, in terms of inner filter algorithm, for example, it's nice. It's really pleasant to ensure these inner filter effects during the EM acquisition in order to be robust in the final interpretation you would like to bring with this the EM. I hope I answered this question.
Okay. Our next question is, what are the technical advantages of EAMS plus absorbance and multivariate analysis compared to the currently used methods for wine analysis, including FTIR and GC-based techniques?
Well, GC-based techniques are really fastidious to implement. So to implement it directly in the winery is not so easy, because you need to not only to dilute your sample, you need also to extract the compounds of interest. FTIR techniques also require some. You don't have the same information with the FTIR. The Aqualog system is really easy to implement and don't require too much sample preparation, which is of interest for the wine professionals, I think. You can also have access to really low concentrated wine compounds, responding in terms of fluorescence emission. You can detect compounds in the range of nanograms and micrograms per liter, which is with a really fast measurement. So it's really nice for when you are looking for qualitative aspects. I also see that combining EM database and multivariate analysis opens a real opportunity to have access to winemaking aspects, from the pressing till the evolution of the bottle.
Okay, our next one is, how readily can the research presented on white wine characterization be transferred to routine industrial application?
Oh, wow. Routine applications. I believe that professional using Aqualog, as the Aqualog can be easily implemented not only in terms of absorbance and color measurements, it can be of interest for them. In one acquisition, they have all these parameters, and they are of interest for winemakers. Perhaps also the detection of microbial spoilage can be of interest if they want to implement that in their wineries, since they want to avoid that problem, since it is nefast for the quality of wine. So all these parameters that are related to to the qualitative aspects of the final product that is going to be in contact with the consumers is of interest for the professionals.
Okay. Are there any international standard methods, such as from the USDA, ASTM, or ISO, that apply to wine analysis, and are these applicable to the Aqualog instrument applied?
Not to my knowledge. I know that OIV, the International Organization of Vine and Wine, has some standards in terms of analytical tools, but combining the fluorescence measurements and the Aqualog instrument, I cannot respond that to you. Perhaps I can ask. In Dijon, in my institute, we have the president of viticulture commission of this organization. Perhaps I can ask him and apply to this and respond to this specific question.
Okay, great. And we have one more. What are the next steps for this research program in terms of future applications to be explored?
This is the nice question concerning 3D fluorescence. I use it since I am in PhD. I think this technique can be of large interest. You can if we want to have accurate precision with in our matrix, like wine, it's a complex matrix. This methodology is of particular importance because you can have access to these fluorophores, and since they are really low present in terms of concentration, you have these. You can easily see them by this methodology. The idea is also to combine other analytical tools that you can really interpret your data in EEM. That's the challenge for the future, and for the wine community, it will be of great interest. I also think that a research program dealing with the qualitative aspects and the sensorial aspects of the final product, and if they can be related to quick vision by EM, would be of interest also. So for me, it's a really challenge to continue and develop this tool and show that the powerfulness of this technique to the professionals.
Okay. What does this tool cost, and what's the total cost of ownership associated with it?
Sorry, Joanne?
Yeah. Dr. Coelho?
Yes, sir.
Did you hear the question? I'll read it. Hi. We'll try to answer that question in an email. We seem to have lost our mic. So this will conclude the webinar. I want to thank everyone for participating. If you have unanswered questions, we can reply to them by email shortly. Just so you know, the webcast will be available for on-demand viewing through April of next year. You'll receive an email from the On24 system to let you know when it's available for replay. It'll also have my email, so you can send any additional questions, and feel free to forward that announcement to your colleagues who may have missed today's live event. We look forward to seeing you next time. Thank you very much. Bye.